I gave you a question there. What we're going to use to integrate that function? Well, of course, it's substitution. And again, it's a good idea to have a think about the structure of the substitution method, just to see what kind of functions can we use this method for. And really, there's two times when you might use substitution. One, you might spot it. You might spot that this is an integral I can do using substitution. And this is usually when you find you've got a function of the form the integral of some function of another function multiplied by what I get when I differentiate the function inside of there. Now it looks horribly complicated, but once you've seen a few of them, you get to recognize them. And the other kind, I'm going to loosely term suck it and see. Sometimes it's worth just having a go at the substitution method to see whether you can get it to work. It might not be so easy to spot as that, but sometimes it will just work out anyway. So let's think about a spot it kind of substitution. Can we think of some integrals which are of this form? Well, the one that I just wrote down will do just fine. So the integral of x times the sine of x squared with respect to x is, roughly speaking, of this form, because you can see here we've got a function of another function. We've got sine of x squared multiplied by something which is almost what we get when we differentiate x squared. If I have g of x is equal to x squared, then g primed of x is equal to 2x. And you can see, well, we've got an x there, so but for a factor of 2, this is exactly of this form. It's a function of another function multiplied by what we get when we differentiate the inner function. Okay, so let's do the integral of this function that we just talked about. Let's apply our substitution method. Okay, so when you're going to do this, you're going to say, well, let's let some variable u equal some function of x, and we're going to choose u is equal to x squared because that's what we've got inside the sine function. And then we take du by dx is equal to 2x. And now, when we're doing the substitution method, and only at this time, you're allowed sort of to treat du by dx as though it's a fraction, just in order to do the rearrangements for your substitution method. Now, du by dx is not really a fraction, it's a differentiation of the function u. But just for the purposes of this, we'll treat it as a fraction, and this is why I like to put this thing in inverted commas. Let's say dx is equal to du divided by 2x. Because when we do a substitution, we need to replace all the x's inside the integral by the u's, and we also need to replace the dx by something involving du. So let's work our way through, and actually I'm going to leave this x where it is. I'm going to do sine of u because I'm going to replace that x squared by u, and then the dx I'm going to replace by du divided by 2x. And you'll realise that actually now I can cancel that x with that x, and that's why I left that x where it was. And so let's just simplify that down once more. So we've got a factor of 2 here, so that's a half of the integral of sine of u du. And you can do the integral of sine of u du. The integral of a sine function is a cosine function with a minus sign in. So it's minus a half times the cosine of u plus our integration constant. Always remember the integration constant. Now the last step is to replace u again with the x squared. So we go back to minus a half the cosine of x squared plus c. And there we go. And always, this is a good little tip. If you're not sure whether you've got the right answer, then you need to differentiate that function back, and you should get what you started with inside the integral sign. So one more example of integration by substitution, just to give you an extra example. This is quite a common type of substitution integral, because I can write it as the integral of x squared multiplied by the reciprocal of 1 plus x cubed with respect to x. And you can see this is a function of a function. It's 1 over the function 1 plus x cubed. And if I differentiate 1 plus x cubed, I get actually 3x squared, which, but for a factor of 3, is the same as x squared. So this is a good candidate for a substitution integral. So without further ado, let's let u equal 1 plus x cubed. Okay, and now we have du by dx, as I said, was equal to 3x squared. And again, treating du by dx as though it's a fraction, we have dx is equal to du divided by 3x squared. And again, I can substitute all these in here. So I'm going to again leave the x squared where it is. 1 plus x cubed is the same as u, so I've got 1 over u. And the dx I can replace by du divided by 3x squared. And you see the nice thing is the x squareds cancel. And so I'm left with the integral of 1 over u du. And you should know what the integral of 1 over u is with respect to u. That should give us a logarithm function. So the answer is the logarithm of the modulus of u plus c. And the last step, again, is to substitute back in for what u is. So that gives us the logarithm of the modulus of 1 plus x cubed plus our integration constant. So this is a pattern you should learn to recognize, actually. If you've got a quotient inside of your integral sign, take a little look, see whether the top, the numerator of the fraction, is related to what you get when you differentiate the bit on the bottom. If it is, then again a substitution method will be the right thing, and you're likely to end up with a logarithm at the end of your integration. One more substitution example, just to illustrate something nice. I said sometimes you just have to suck it and see with substitution. Sometimes you just have to try something and see whether it works. So let's do the integral of x times x plus 4 to power 3 with respect to x. Now, if you've been paying close attention, you realise this is an integral I've done once already. I did it using integration by parts. But let's just try and see whether we can do it by substitution as well. Well, let's try saying, let's let u equal x plus 4. So du by dx is equal to 1. Let's rearrange that. So we get dx is equal to du in inverted commas. So, okay, and actually I've got an x plus 4 here for u, so I can rearrange that and say x is equal to u minus 4. Okay, so let's substitution for everything. So we end up with the integral of wherever I see an x, I can put a u minus 4. Multiplied by x plus 4 cubed, that's the same as u cubed. And wherever I see a dx, I can put a du. There we go. And I can multiply this out. So I end up with the integral of u to the power 4 minus 4u cubed with respect to u. Oh, that's easy now to do, that integral. So I can integrate u to the power 4. That gives me u to the power 5 over 5. Minus integral of 4 times u to the power 3 is u to the power 4 plus our integration constant. And then finally I substitute back in for what u is. So let's do that, and we end up with x plus 4 to the power 5 divided by 5 minus x plus 4 to the power 4 plus c. And that there is our answer. Some of you might be looking at that and thinking, that doesn't look exactly like you got before. Before, I got x times x plus 4. Let me make sure I get this right. To the power 4 divided by 4 minus a 20th of x plus 4 to the power 5 plus c. Is that the same as that? Turns out it is, but you have to do a little bit of playing around with the algebra to show it is. So I'll leave that for you. Is that the same as that? Can you show it's true?